Hello again, physics friends. Last time we were talking about length contraction, we actually learned about length contraction in the context of this rocket and the racetrack problem. And we found that in order for the finish line clock to be able to reach Alice, moving at 3/5 c in 80 nanoseconds, it could not be the full length of 60 feet away. It had to be at most 48 feet away. So the rest length of the racetrack used to be 60 feet, but what we found was that if you're moving at 3/5 c for 80 nanoseconds, you're only going to travel 48 feet. So the finish line clock was only 48 feet away, which means that the racetrack is only 48 feet in the rocket frame, only 48 feet long in the rocket frame. So we kind of talked through the need for length contraction in the context of that problem using numbers. Here we're going to repeat that process, but using symbols to basically derive an expression for length contraction. And we already know that that expression is that the moving length is equal to the rest length divided by gamma. So the goal today is to derive that relationship. And we're basically going to start with exactly the same configuration, but instead of putting in numbers, we'll put in symbols. So let me get that set up. Okay, so as you can see, we've now labeled the rest length of the track to be L naught, and we've erased all the times. Instead of labeling the track's length in the moving frame as a particular number, we'll label it L. And instead of saying that the velocity is 3/5 c, we will just leave it as v. And then specifically, we'll call the velocity of the rocket VRT, the velocity of the rocket relative to the track. And in the rocket frame, we'll call that velocity VTR, the velocity of the track relative to the rocket. All right. The other thing we want to point out is the following. So we have VRT is the velocity of the rocket relative to the track. VTR, which is minus VRT by reciprocity, is the velocity of the track relative to the rocket. But how about the speeds? Well, recall that the speed is the magnitude of the velocity. And so the velocity of the rocket relative to the track has a speed, which is its magnitude, and the velocity of the track relative to the rocket is also the magnitude of, has a speed rather, which is the magnitude of that quantity. And since one velocity is equal to minus the other, their magnitudes will be the same. So instead of carrying around all of these subscripts, we will just call the speed, for the speed, we'll just call it v with no subscript, and we'll understand that v is a positive number. Okay? Good. And we're going to use that when we talk about distance traveled equals speed times time elapsed. So the first thing that we'll do is we'll notice that in the track frame, we want to find the readings on these two clocks. In the track frame, the elapsed time is going to be equal to the distance traveled by the rocket, which is L naught, the full length of the track, divided by the speed of the rocket. And we just said the speed we'll just call v. So what that means is in these clocks, we can write L naught over v, because that is the elapsed time in the track frame, right? So both of those clocks started at 0. This amount of time has elapsed, so the new reading will be 0 plus L naught over v, which is just L naught over v. The reading, though, on the rocket itself is going to be smaller than that because the rocket's clock is moving, and so less than L naught over v will have ticked off on that moving clock. How much less? Well, that reading will be L naught over v divided by gamma. That's by time dilation. Okay. So what that means is in the rocket frame, when the finish line clock reaches the rocket, the reading on the rocket will be L naught over v all over gamma, and the reading on the finish line clock will be L naught over v. So we can put those numbers in, L naught over v down there, and up here it will be L naught over v all over gamma. And now we have all we need to show that the length of the racetrack is L naught over gamma. Okay. And how do we do that? Well, let's see. The finish line clock has to travel a distance L, and the elapsed time is L naught over V all over gamma, because the rocket's frame clock went from 0 to that value. And the speed of the finish line clock is V. So what we can say then is that we know distance traveled by finish line clock is equal to speed of clock times elapsed time. Okay, that distance traveled is L. The speed of the clock we said was V, and the elapsed time is L naught over V all over gamma. Well, the V's will cancel, and then you're left with L equals L naught over gamma. So the length of the racetrack in the rocket frame is smaller than the racetrack's rest length by this factor of gamma. And that's all we need to do to show this in general. You know, we showed it numerically in the previous version of this problem, and here we got rid of the numbers, kept the symbols, and have the general result that the length of the moving object is smaller than its rest length by this factor of gamma. All right, until next time, my friends, take care and be well.